Hello friends, so this is part 2 for the year 2021, and in part 2 we are going to solve 10 questions, and all these 10 questions are from the mains. So first question, find out the surface charge density at the intersection of point x equal to 3 meter plane and x-axis in the region of uniform line charge of 8 nanocoulomb per meter lying along z-axis in the free space. So we are given that we are having a line charge and it is lying along z-axis, and we have to find out the surface charge density at the intersection of point x equal to 3 meter and our x-axis. And with the basic formula we know that electric field due to a line charge due to line charge, that is our E will equal to lambda 2 pi epsilon naught multiplied by R. And from here, if you substitute the values, lambda is given to us 8 nano coulomb, 10 to the power minus 9, and 2 pi epsilon naught. Epsilon naught is 8.85 into 10 to the power minus 12, and at a distance of 3 meters. So we get this electric field is approximately equal to 47.9 volt per meter. And so we found out our electric field at a distance of 3 meter, which is through a line charge which is having a charge density of 8 nano per coulomb. But in this case, we are supposed to find out the surface charge density on the plane in a free space. Okay, so we can just write the formula that surface charge density on a plane in free space and that is, suppose our sigma will be equal to epsilon naught multiplied by the electric field which we just found out. Epsilon naught we know is our 8.85, 10 to the power minus 12. Electric field is our 47.9. So this gives us that the surface charge density will be equal to approximately 4.24 into 10 to the power minus 10 coulomb per meter square. And nanocoulomb, because all this will be becoming as 0.424 nanocoulomb per meter square. So option number 1 is the correct one. 1 is Correct. Next question. We are given in a parallel plate capacitor setup, the plate area of capacitor is 2 meter square and the plates are separated by 1 meter. If the free space between the plates are filled with the dielectric material of thickness 0.5 meter and area 2 meter square, the capacitance of the setup will be dash epsilon naught. Dielectric constant of the material is 3.2. So in this case, we are given that we are having a capacitor, parallel plate capacitor, and area of capacitor is suppose A and D is the distance between the plates. Now in the second case, the space between the capacitors is filled with the dielectric and the thickness of dielectric is 0.5 meter. Initial space is our D is given as 1 meter. So obviously the dielectric is going to cover half of the space. So we can just draw the half of the space. So this is the dielectric, and let us suppose the dielectric constant is given as K. And we assume that the C1 is the capacitance for the part of a dielectric and C2 is the remaining part which will be consisting of air as a dielectric. And let us suppose the thickness is of this is our D1 and this thickness is our D2. We can later on substitute the values. Therefore, we can write that C1, which is our capacitance with dielectric, C1 will be equal to K epsilon naught A upon D1. Area of the plates in the both cases is same. So we can find out value of C1. K is given to us as 3.2 and we have epsilon naught because the final answer is in form of epsilon naught, so we will keep it like that, and area is 2 and the D1 is our 0.5. So we get our C1 is equal to 12.8 times epsilon naught. And similarly, we can find out the capacitance with air. Capacitance with air, which we assumed is of C2, is equal to epsilon naught A divided by D2. So we can find out value of our C2. C2 will be equal to our epsilon naught. Area is 2 meter and distance is our 0.5. So this gives us 4 times epsilon naught. And both capacitors C1 and C2 are connected in series. So we can say the equivalent capacitance one upon C equivalent is equal to 1 upon C1 plus 1 upon C2. We substitute the values. We get this as 1 upon C equivalent will be equal to 1 upon 12.8 times epsilon naught plus 1 upon 4 epsilon naught. Epsilon naught we can take as common, and inside we are left with 12.8. So we can take this LCM 12.8 will be LCM, and it comes as 1 plus 3.2, which comes as 4.2 12.8 times epsilon naught. And from here we can see our C equivalent will be approximately equal to 3.05 epsilon naught. So we can see this is equal to our 3.05 times epsilon naught. Next question. It states that for changing the capacitor of a given parallel plate capacitor, a dielectric material of dielectric constant K is used, which has the same area as the plates of the capacitor. The thickness of the dielectric slab is 3/4 times D, where D is the separation between the plates of parallel plate capacitor. The new capacitance is C prime in terms of original capacitance C naught is given by the following relation. So in this case, once again we are having two capacitors. A is the area plates and D is the distance between them, and its capacitance is given as C naught. In the second case, a dielectric is introduced between the plates and its thickness is given by 3/4 by D. So this is the dielectric and its thickness is 3/4 by D. So remaining will be D/4. And we can assume, so it will be consisting of two capacitors now. One will be which is having a dielectric, let us call this C1, and other one is without dielectric, that is with air, let us call this C2, and both of them will be in series. So let's find out capacitance with dielectric. Capacitance with dielectric, that is C1, will be equal to K epsilon naught A, and this is 3D/4. So from here we can get our C1. C1 will be equal to, this comes as 4/3, and we have this is K epsilon naught A divided by D. Similarly, we can find out capacitance with air. Capacitance with air, which we said will be C2, is equal to K epsilon naught A, and the distance between them is our D/4. Therefore, we get our C2 will be equal to 4 times, sorry, there is no K. This comes as 4 times epsilon naught A upon D, and both of them are in series, and when they are series, this new capacitance is given as C prime. Therefore, you can say the equivalent capacitance will be 1 upon C prime is equal to 1 upon C1 plus 1 upon C2. We substitute the value, we get this as 1 upon C prime is equal to, we have this as 4K epsilon naught A, and this comes as our 3D plus 4 epsilon naught A, and this is our D, and we can just take common, so we get this as D upon 4 epsilon naught A, and we are left with this as 3 by k plus 1. So we get our C prime will be equal to, this is our 4 epsilon naught A, and this is D, and we get this as 3k plus 1. So this is new capacitance, and original capacitance was C naught, and this C naught will be equal to, we can say our C naught will be equal to epsilon naught A upon D. So we can just find out their ratio. So C naught, let me rewrite this equation. We can write this will be 4 upon 3k plus 1, and this comes as our epsilon naught A upon D, and this is nothing but our C naught. So this comes as 4 3k plus 1 times C naught. Okay. So we get this as, okay, we can take k as LCM. So we get this as C prime will be equal to 4 times k, 3 plus k times C naught. This is 4k divided by k plus 3 divided by C naught. So option 3 is correct. Correct. Next question. It is given a simple pendulum of mass m, length L and charge plus q, suspended in the electric field produced by two conducting plates as shown in the figure. The value of the deflection of the pendulum in equilibrium position will be. Basic figure is given to us. So we have a parallel plate capacitor, and in the T half we have a dielectric of constant K, and the other half is of our not half but of some thickness, that is of air. So this thickness will be our D minus T. So here we are having basically two capacitors. We can just draw its equivalent, and this is first which is going to have dielectric, and this is a second one. Okay. So we are having a dielectric, let us call this as C2, and this is air, with air as a dielectric, this is C1. On the one end it is having a plus V2, on the other end it is having a minus V1. So this is the basic circuit for that. And there is a pendulum. So, and this pendulum is our with respect to C1. So let us draw with respect to C1, and if this is the mean position, then the pendulum will be pulled in this direction, and its force will be our plus Q times E. In the downward direction we are going to have our mg, and there will be a tension T here. Let us suppose this angle is our theta, which we are supposed to find out value of the deflection, and this T we can divide into two components. So this angle will be also theta, so we get this as T cos of theta, and we are going to have a T sine of theta, and this entire setup or movement is in the distance of D minus T, which we are called as C1. So this is our entire capacitor C1, and if E is the electric field, so we can just balance the forces, because it is said that pendulum is in equilibrium. Therefore we can write that T sine of theta will be equal to Q times our electric field, and we are going to have T cos of theta will be equal to our mg. If we divide them, we are going to get tangent of theta will be equal to QE upon mg. Okay, so this is the first half, and in the second half we have to, because the solution is in terms of the our voltages as well as the capacitance. Okay, V1, V2, C1, C2 and D minus T, that is the distance between the plates. So let's find out what will be our C1 and what will be our C2. So we can say our C1, which is for air, will be equal to our epsilon A D minus T, and C2 will be equal to our K epsilon A divided by T. C2 is for dielectric and C1 is for the air. And next we can find out the, because we need to electric field. So for the calculation of electric field, we are first of all going to find out the total voltage difference across the plates. Voltage difference across the plates, and let us call that V. So V will be equal to, this will be coming as V2 plus V1, because V1 is of negative sign. Now we have to find out our respective voltages. From the figure we can clearly see that C1 and C2 are in series. C1 and C2 are in series. So it means they are going to have the same charge. Same charge. Let us suppose that charge we called as Q. And the potential difference across C1 is suppose V1, and across V2 is suppose V2. So we can say voltage across C1 is suppose V1, and voltage across C2 is suppose V2. Thus, like I said, that they are going to have same charge. Therefore, this value of charge Q will be equal to our C1 V1, and which we can also see is our C2 times V2. But we know that the total voltage suppose that is given as V, will be equal to VC1 plus VC2. And one second. Okay, let me call this as VC1 and VC2. Later on we can just substitute them. And from here I can say that my VC1 will be equal to Q upon C1, and my VC2 will be equal to Q upon C2. So we can substitute value of VC1 and VC2. We get our voltage V, total voltage, that is our Q upon C1 plus Q upon C2. Q we can take common, so this comes as 1 upon C1 plus 1 upon C2. So from here we can find out our charge Q. Therefore we can say our charge Q will be equal to V upon 1 upon C1 plus 1 upon C2. And this can be written as V, and we take LCM. This comes as C1 C2 times divided by C1 plus C2. Now voltage across the capacitor C1 voltage across capacitor C1, which we called as VC1, will be equal to Q times C1. Q we just found out, we substitute the value, so we get our VC1 is equal to, this comes as 1 upon C1 times V times C1 C2 and C1 plus C2. Here C1 and C1 cancels out, so we get VC1 will be equal to C2 C1 plus C2 times V. And we know that our this V is equal to V1 plus V2. So we substitute it, we get our VC1 is equal to C2 C1 plus C2 times V1 plus V2. So this is the voltage across capacitor C1, and which is nothing but our air. Please remember, this is the voltage of the capacitor which is of air. Therefore, we can find out the electric field. Electric field in the air region, which we called as E, or we can also write this is E air, which we called as our E, because force we called as Q multiplied by E. E air will be equal to voltage of our VC1 divided by D minus T, or which we can also say as a V of air divided by D minus T. V of air we just found out is our C2 C1 plus C2, and this comes as V1 plus V2 divided by D minus T. So we found out our electric field. This will be giving us the applied the force due to electric field. Therefore, we can say that the electric force which we called as our F will be equal to Q times our E air, or we can say Q times our E. We substitute value of E, that is the electric field, we get this as the force will be equal to Q, and this is our C2 C1 plus C2, and we have here V1 plus V2 and D minus T. And tangent of theta we just found out is our QE divided by mg, and we found out of electric field. Okay. Therefore, we can say that tangent of theta is our force due to electric field divided by mg, and force due to electric field we called as F, and we receive mg. So we substitute it, we get this as Q upon mg and this is C2 C1 plus C2, and we have this as V1 plus V2 d minus d, and we are supposed to find out theta. So we can say our theta will be equal to tangent inverse of Q upon mg C2 C1 plus C2 times V1 plus V2 and d minus d. So the option number is V1 plus V2 and option number 3 is correct. Option 3 is correct. Next question. It states that two capacitors C1 with capacitance 2C and C2 with capacitance C are connected in parallel. They are charged and the battery is removed. If a material of dielectric constant K is inserted in C2, find the potential across them. So obviously if they are parallel, the potential across them should be same. So initially they are connected in parallel. So we are having two capacitors and they are connected in parallel with a voltage source. So this is our C1 which is given as 2C. We have C2 which is given C, and there is a voltage source V to it. And they are charged. So let us suppose the charge on C1 is Q1 and on C2 it is Q2. Later on the battery is removed and dielectric constant K is inserted in C2. So for C1 there is no change. So C1 is a C1, and in C2 we have now a dielectric constant K. Let us suppose its capacitance is now given as C2 prime. And we have to find out the final potential across the capacitor. So final potential across the capacitor should be same. And in this case, the charge, because battery is removed, so charge should be same initially and final condition. So this is our initial condition and this is our final. So let us start with initial condition. Initial condition is basically without dielectric. Therefore, we can find out charge on C1 . Charge on C1, let us suppose that is our Q1, will be equal to C1 times V, which is applied voltage, and C1 we know is our 2C, so this comes as 2C multiplied by V. Similarly, we can find out charge on C2. Let us suppose that is our Q2, and it will be equal to our C2 times V. C2 is our C, so this comes as C times V. Now we find out the total charge. Total initial charge, let us call this as Q, will be equal to Q1 plus Q2. This comes as twice CV plus CV. This gives us total initial charge, that is our Q, is equal to 3 times CV. Now our dielectric is introduced, that is our final condition. Final condition, which is basically with dielectric in C2, and we have to remember total charge remains constant. Total charge remains constant, which basically is Q, and we found it there 3 times CV. And we can find out new capacitance of C2. New capacitance of C2, let us call this as C2 prime, that will be equal to K times the original capacitance, that is C2. And C1 is same. C1 is our 2 times C. And still the capacitors are connected in parallel, so therefore their, you can say, potential will be same on both. And we can say that like I said, the total charge will be constant, so you can say total charge before, or we can say total charge initially will be equal to total charge finally. Initial charge we know is our Q, and final, let us suppose we have a Q1 prime plus Q2 prime, and we can easily find out a Q1 prime and Q2 prime. So a Q1 prime is our C1, and if final voltage is VF, C1 is still equal to our 2 times C, so this comes as 2C times VF, and our Q2 prime will be equal to C2 prime times VF, and C2 prime is K times C2 VF, and C2 we already know is our twice C, so this comes as K 2C multiplied by VF. Substituting this equation, we get Q is our total initial charge, which we found out is 3 times CV is equal to Q1 is our, sorry, one second, C2 is C, not 2. So we get this as 2C VF plus K C times VF, and CVF we can take common, so this comes as 2 plus K times C and final voltage VF. This C and C we can just cancel out, so from here we get our final voltage will be equal to 3 divided by 2 plus K times initial voltage, that is our V, and this comes as option number B is correct. B is correct. Next question. We are given the 2-point charges are suspended from a given point as shown in the figure. Find the equilibrium separation between them. So basic figure is given to us. We have charges, both are same, so they are going to repel each other, and the distance between the two is given as x. Angle is given theta, so this will be over x by 2 and other part will be also over x by 2. We have to find out the separation, means we have to find out the value of x. Okay. So we can just take one of the charge and draw the forces on it. So let us suppose this is charge q. So we have a force that is a F, force of repulsion. In the downward direction we are going to have mg, and this is our tension T, and with respect to equilibrium vertical it is making angle theta. Therefore this angle will be also theta, so we can say we are going to have this as T cos of theta, and this will be our T sine of theta, and the length of this is given as L. So we can just equate the forces. We get this as T sine of theta will be equal to F, and T cos of theta will be equal to mg. If we divide them, we get this as tangent of theta will be equal to F upon mg, and our F will be equal to K, and we have this as Q square upon X square divided by mg. So we can write this as K Q square X square by mg, and okay, there is no need to find out tangent because the options are in sine, cos and tan, so we simply find out our value of x square. So we can say our x will be equal to, we have this as K Q square mg tangent of theta and its square root. Q we can take common, and 1 upon tan is our cot, so we can write this as K cot of theta divided by mg and its square root. And K is our 1 point, let me write it here, this is multiplied by 4 pi epsilon naught. So we get this as cot 4 pi epsilon naught. Option number B is correct. B is correct. Next question. We are given equivalent capacitance of the following arrangement of the identical parallel plate is. Basic figure is given to us. We have plates, parallel plates rather. Distance between them is D, 2D and 3D, and the dielectric constant is given as K, 3K and 5K. Area of the plates is same, that is our A. So we can just draw its equivalent, and the equivalence will be, so this will be our first part, it is short circuited with the second part and the short circuited with the third part. So let us suppose this is C1, C2, C3. Dielectric is K, 3K and 5K. Distance between plates is D, 2D and 3D. Area of the plates is entirely same. So all these capacitors are connected in series. So we just find out the equivalent capacitance. Equivalent capacitance, and we can write the formula 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, and C1 is our K epsilon naught D, epsilon naught A, and divided by D, plus C2 is our 3K epsilon naught A, and this is our 2D, plus similarly this will be 3D, and we have this as 5K epsilon naught times A. And we can just take common, so it's quite straightforward now, and this comes as D upon K epsilon naught A 1 upon 2 by 3 plus 3 by 5. So LCM will be over 15. So this comes as 15 plus 10 and plus 9, which comes as 34. So we can write this as D K epsilon naught A multiplied by 34 upon 15. So we get our C equivalent will be equal to, this comes as 34D, and we are left with 15K epsilon naught A. So this is our equivalent, and option number C is correct. Option C is correct. This question is typically, you can say, insertion of a conductor inside the plate. Okay, if we are having two plates and we insert a conductor inside these plates, so this is similarly given in the same way, but a question represented in a different point of view. Okay. Next question. We are given two dipoles P1 and P2 are perpendicular to each other, are placed in a uniform magnetic field such that P1 makes 37 degree with the field. Both dipole experience same torque. Find the ratio of their dipole moment. So basic figure we can draw. So we are given that we have electric field. Suppose in this direction, P1 is making an angle of 37 degree with the dipole. So this is our P1 making an angle of 37 with the dipole, and P2 is 90 degree to P1. So this will be over P2 such that this angle is 90 degree. So we have this as P2. So obviously this angle will be over 53. And we own torque in both the cases same. So general formula for the torque, we know that the torque experienced by a dipole in electric field, torque experienced by the dipole in electric field, that is given as tau is equal to dipole moment times electric field and sine of theta, angle between electric field and this. So we can divide this formula into two parts. For first we can say our tau 1 is equal to P1 E sine of theta 1, and then we can say our tau 2 is equal to our P2 E sine of theta 2. and both torque are given same, so we are given that our tau 1 is equal to tau 2. So we substitute the value, we get this as P1 E sine of theta 1 is equal to P2 E sine of theta 2. So E and electric field cancels out. We need to find out the ratio of dipole P1 by P2. So we can say that P1 by P2 will be equal to sine of theta 2 and sine of theta 1. So we substitute the value, we get this as sine of 53 divided by sine of 37. So we get this as 0.8 divided by 0.6, which comes as 4 by 3. Sine of theta 1 37. Okay, so this is the ratio of P1 by P2, that is 4 by 3. Option A is correct. Next question. We are given the electrical permittivity of the dielectric varies with X as if the area of the plates is A, then find the capacitance of the capacitor. So permittivity is given by these two equations. So because if we consider D is the distance between the plates, then in the first half, that is from, suppose this is 0, from 0 to D by 2, and we are having a permittivity that is governed by this first part, and the second part is governed by this. Okay. So here, let us suppose A is the area of the plates, and let me write the equation. So I can write this permittivity dependent upon X will be equal to epsilon naught 1 plus k x by d, and second part is our A of x is equal to epsilon naught 1 plus k d minus x divided by d, and this is for 0 less than equal to x less than equal to d by 2, and then it is our d by 2 less than equal to x and less than equal to d. And from the figure, from this equation, we can clearly see that there is a symmetric profile of our permittivity. First it increases, then it is going to increases linearly up till middle, and then it decreases linearly. Therefore we can write that this form a symmetric profile of permittivity increasing linearly to the middle, and then decreasing linearly. In this case, we can consider that, let me redraw the figure here. So we consider you can say a series of infinite thin capacitors of thickness dx. Let us suppose, which I mean that we consider a infinite thin capacitors, that is dx, thickness dx, and area is our A. Okay. And we can consider it from here, this is our 0 and this is our D. So from entire this region we can consider small parts and they can be added. And its capacitance is, let us suppose, given as DC. And its permittivity is, suppose, our E of x. So we can write that capacitance of infinite so let's write that considering a series of thin capacitors of thickness dx and permittivity epsilon x. So we can say that capacitance of this thin capacitor of thin capacitor, let us call this a DC. So we can write the formula that our DC will be equal to epsilon x times A and divided by dx. And from here we can capacitance, okay, and from here we can write that the small potential across the capacitor, this thin capacitor, will be over dx divided by epsilon x and multiply by A. So we can find out the total potential difference. Total potential difference, if that is given as V, which will be equal to integration from 0 to D entire thickness, and this is our dx divided by epsilon x multiplied by area A. And in terms of capacitance, we can also write this as 1 upon C will be equal to 0 to D, and this comes as our dx and epsilon x multiplied by A, so which gives us a C will be equal to we need to find out 1 upon C. Let's keep it like that one. So 1 upon C. Now this our permittivity is having two different profiles. So accordingly we just change the limits of integration. So first will be our 0 by d by 2, and we have this as dx epsilon naught plus k upon d times x, and second is our d by 2 up till d, and this is our dx. And one second, this is let me correct the equation. Epsilon naught k epsilon naught, yes, this is our epsilon naught x, and this comes as our epsilon naught plus k d minus x times epsilon naught divided by d. So we can just integrate it, and that integration will be because both integration will be coming as same, because we can, one second, this is our d, so this comes at d by 2. Okay, both will be coming same because in the one part it is d minus x, so value of x will be our d minus d will be giving us 0, and other part is our d by 2. Okay, so this will be giving a d minus d by 2, giving us once again d by 2, which will be same of this first part also. So we can say that both integrals are same, so we can write 1 upon c, this will be over 2 upon a, and we get this as 0 to d by 2, and this comes as our dx epsilon naught plus k epsilon naught x upon d. And so rest terms are constant, so we are interested in this part, so let me write it separately. So we can say this as integration, and this will be over dx, and here we have our epsilon naught k epsilon naught x upon d, which will be giving us this will be our a plus bx. A plus bx is natural log of a plus bx. So we get this as natural log of epsilon naught plus k epsilon naught d times x, and the limit are from 0 to d by 2. 0 to d by 2, and we have this as multiply by 1 by b, and 1 by b will be coming as 1 upon k epsilon naught upon d. Okay, so we can just substitute the limits, and we get this as 1 upon c is equal to 2 upon a, and this comes as d upon k times epsilon naught, and we have here natural log of lower term 0 0. Okay, so we have this as natural log of epsilon naught plus this will be over k epsilon naught d by 2 divided by d and divide by epsilon naught. Epsilon naught, epsilon naught, epsilon naught cancel out. This t goes with d. Therefore, we are left with 1 upon c is equal to 2d k a epsilon naught. Natural log of this comes as 1 plus k divided by 2. And options are given to us. Yes, they are given. So let me write C, hopefully. So from here I get that my C will be equal to K A epsilon naught divided by 2D and 1 upon natural log, and this will be coming as 2K, 2 plus K divided by 2. I think one term is missing here. That is our, I think epsilon naught is missing. Something is wrong. Let me check. 1 plus kx, kx, kx. Okay, this is correct. This is ex, epsilon naught. I think let me check whether this second part is correct or not. From the looks of it, I think something is missing. Okay. I think this equation I have written, I'm not sure it's correct or not. Yes, so this equation I have written is incorrect. Okay. And it should be, that's why the problem is. Here it is epsilon naught. It is not a product, but it is simple addition. And and in the denominator there is no d. Therefore here also there is no d, here also no d, no epsilon naught, and here also no epsilon naught, no d, no d, no epsilon naught, no d, no epsilon naught. Now it is making some sense. So there is only k times x, and here also k times x, here also k times x. So here also it will be now only k, and rest of things are now so this comes as 1 upon k, and we have this a natural log of epsilon naught plus k d by 2, and this comes as minus natural log of epsilon naught. So this comes as k and divided by epsilon naught. Now it's correct. Here also there is no this is a. Now it's correct. Sorry, I think there was some problem with the equation. So we can say this is equal to over C is equal to, we can write this as Ka divided by 2 1 upon natural log of 2 plus Kd upon this, we can write 2 epsilon naught divided by 2 epsilon naught. Now I think the answer is going to match. Yes, option B is correct. B is correct. Next question. We are given an inclined plane making an angle of 30 degree with the horizontal is placed in a uniform horizontal electric field 20 Newton per coulomb as shown in the figure. The body of mass 1 kg and charge 5 millicoulomb is allowed to slide down from the rest at a height of 1 meter. If the coefficient of friction is 0.2, find the time taken by the body to reach the bottom. G is said to be 9.8 meters square, sine 30 and cos 30 is given to us. So we can just, it is sliding downward and there is a friction also. So we can just draw the basic figure for that along with all the forces. So this is about 30 degree and we having a mass m. So obviously in the downward direction we are going to have our mg, and this mg we can divide into two components. So this angle will be also over 30. So we are going to have mg cos of 30 and we are going to have mg sine of 30. And our electric field is in this direction from left to right. So we can just divide this electric field also into two components. And so first component will be parallel to the plane, inclined plane rather, and this angle will be our 30, so we get this as E cos of 30, and second component will be in the same, that is our mg is our E sine of 30, and there will be one force that will be our normal. So these are the forces, and the friction will be acting in the upward direction. So we are going to have a frictional force. Let us suppose that is a Fr in the upward direction, and it says that it is moving in downward direction. Let us suppose the acceleration is given as A. So from here we can write that our normal n will be equal to mg cos of 30 plus, sorry, this is not electric field but charge time electric field force, my mistake, and we get this as QE sine of 30 sine of 30. If we substitute the values, we can find out normal, that if a normal mass is given to us as 1 kg, so this comes as 1 multiplied by 9.8, cos 30 is also given to us square root of 3 divided by 2, plus charge is our 5 milli 10 to the power minus 3, electric field is our 200, and this is our 1 by 2. So our normal will be coming approximately equal to 9 Newton. We can easily find out our frictional force. Frictional force will be equal to coefficient friction multiplied by normal. Coefficient friction is given as 0.2 multiplied by normal. This gives us 1.8 Newton. Now body is moving in the downward direction. Therefore we can write the equation that the net force on the body is, suppose, our F, which will be acting in downward direction. So we are going to net force as F because it is moving along the inclined plane in the downward. So we are going to F mg sine 30 minus QE cos 30, and we have frictional force also in upward direction. So net force F will be equal to m mass into acceleration, which will be equal to, and value we know is our 1 into 9.8, sine 30 is our 1 by 2, minus charge is given as 5 into 10 to the minus 3 into 200, this is root 3 by 2, and friction we found out is 1.8. Therefore we can say that our mass is our 1, so we can just ignore it. So we get our acceleration will be equal to, this will be 2.34 meter per second square. And it is said, find the time taken. Okay, So it is moving down the inclined plane. From a height which is given to us as h, and let us suppose it starts from this point, and the distance covered by this is suppose our s, and this angle is our 30. So we can easily say that our distance along the inclined plane incline is our s. So we can write that our s will be equal to, there will be h upon s is equal to sine of 30. So s will be equal to h sine of 30. Height is given as 1, so this comes as 1 upon sine of 30, that is 1 by 2, which is about 2 meters. Initially it was at rest, so initial velocity is over 0. So we can use the kinematics formula that our s is equal to ut plus half at square, and sv is over 2, u is 0, so this equation goes away, and this is half acceleration is over 2.34 multiplied by t square. So we get this as t square will be equal to 4 divided by 2.34. So t will be equal to 2 divided by 2.34 and its square root, which gives us that value of t is approximately 1.3 seconds. Time taken is 1.3 seconds. So this completes the part 2, which covered 10 questions from the year 2021. In the first part also we covered 10 questions. So the remaining questions we are going to cover in part 3 as well as part 4 if required, and that will be consisting of combination of both mains as well as advanced. Okay. So this completes the part 2. Thank you.